Today's seminar is going to focus on solutions to systems of linear equations, and our goal, or I can statement for this lesson is, I can identify the number of solutions a system of linear equations has by solving it. And by solving it, I mean by either using graphing, substitution, or elimination. So go ahead and pause the video at this time and copy this title as well as the goal into your notebook. Okay, so you should have that copied down. And your foldable will look like this. We're going to look at systems of linear equations that have one solution by using graphing as well as substitution or elimination. Systems of linear equations that have no solution by graphing and using substitution or elimination. And systems that have infinitely many solutions by both graphing and using substitution or elimination. So let's go ahead and get started. So the methods that we're going to use are going to be the same as from last week, using both graphing, substitution, as well as elimination. We're just going to have an extra step here, and it's going to be identifying the type of solution that the system has. So let's start with one solution, and we'll start with the graphing problem. And this is going to require some of the skills that we've used previously. So since this is graphing, we're going to want to make sure that our equations are in slope-intercept form. And currently, they are in standard form. So that means we're going to have to switch these. So they should be in the form of y equals mx plus b. That's why we need to change these two and then graph them. So the first one, let's change that. So x minus 3y equals negative 9. So our job here is going to be to get y by itself. So first and foremost, I'm going to subtract x from both sides. These will eliminate or cancel each other. Negative 3y equals. Now, when you're writing these down, put your x first, because otherwise it won't be in the form that we use for slope-intercept form. It will still be in that form, but it won't look as nice. So negative x minus 9. And last but not least, what we're going to have to do here is divide by a negative 3. Everything by a negative 3. So I'm just going to write that this way so that I don't forget. And my solution here then is y equals negative 1 divided by negative 3 would be a positive 1 over 3. So 1 over 3x. Negative 9 divided by negative 3 would be plus 3. So that's our first equation switched over to slope-intercept form. Now we have to do the same with the second one here. So rewrite my equation, x minus y equals negative 1. Again, trying to get y by itself, so subtracting x, reorder this, so we would have negative y equals negative x minus 1. And when you're rearranging, make sure you're keeping the sign with the numbers so that you don't come up with a different type of line. And here we're going to divide by negative 1, divide by negative 1, and divide by negative 1. Negative 1 divided by negative 1 is positive 1, so y equals negative 1 divided by negative 1 is a positive 1, so I'm just going to write x here, but remember in front it's 1 over 1. And then negative 1 divided by negative 1 is a positive 1, so y equals x plus 1. We now have both lines in slope-intercept form, so that means we can graph them. So this line I will do in red, and this line I will do in blue. So if I'm graphing this one, I'm going to plot at positive 3, because that's my y-intercept. And my slope is up 1, right 3, up 1, to the right 3. We have 3 points in order to make a line. We only need 2, but we use 3 to check. Use a straight edge to ensure that we get the right intersection point on this one. And then my last one here would be at 1 for my y-intercept, and the slope is 1 over 1, so up 1, right 1, up 1, right 1, up 1, right 1. Just did a few extra there, so we got to the point of intersection. Draw our line through there. And it looks like we do have an intersection point here, so that means this has one solution. And that solution is at the point, looks like 3, 4. So that's graphing with one solution. Sometimes we might be using elimination or substitution, and that can also give us a one solution problem, which is what we've been working with. So let's go ahead and bring this one back here in case you didn't quite get all of that. But let's move over to one that is going to use substitution or elimination. So at this point, I don't really have a preference, but I want to use the method that's going to be the quickest here. And since this one's already set up where both of them are in standard form, I think that using elimination would be my best option here. So we're going to use elimination. Since it's set up in that form, for substitution it would take a little extra work. We want to be as efficient as possible, so we're going to go ahead and do elimination. So I'm going to rewrite my problem. 2x plus 5y equals 14, and 6x plus 7y equals 10. Now remember, with elimination we want to try and eliminate one of the variables. So we can go through the different things that we learned from last week. So we could think, can we add any of these things to cancel them? Well, no, they won't cancel out. Can we do subtraction right away? No, they won't cancel with that. So we're going to have to use some multiplication first, even before we can do addition or subtraction in order to eliminate. What I see here is 2 and 6, and I can make this 2 a negative 6 by multiplying both sides by a negative 3. That would be the quickest way to do that. So if I multiply that through, I'm going to rewrite this equation next to it. So I would have negative 6x minus 15y equals negative 42. And then the bottom equation we would just copy down again. 6x plus 7y equals 10. And now it looks like we can use addition in order to eliminate. So negative 6 plus 6 is 0. Not even going to write that down. And then we would have negative 15 plus 7, which would give me negative 8y. And that's going to be equal to negative 42 plus 10 would be negative 32. So we're going to solve for y here. Divided by negative 8, divided by negative 8, which would give us a positive 4. So we got 1/2 of our solution, y equals 4. So if I put solution, we know that y is 4. So now we're going to use a little bit of substitution, remember, and put this 4 in for y, and it has to go into one of my original equations. I think this top one's going to be easier to work with, so I'm going to go ahead and substitute y in, or 4 in for y, in 2x plus 5. So 2x plus 5y equals 14. We're going to substitute that 4 in for y. So we're going to have 2x plus 5 times 4, and that's going to equal 14. So let's do our multiplication here and then solve. So 2x plus 20 equals 14. I would want to subtract 20 from both sides, so I'm going to try and make that fit here. And once I do that, these 20s will cancel, so I'd have 2x equals 14 minus 20 would be negative 6. Divide by 2, x is equal to negative 3. So negative 3. My solution here is negative 3, 4. Oh, and that's kind of off the paper here. Sorry about that. Solution is negative 3, 4. And of course, if these do intersect, then they have one solution. So those are examples that we have been working with. So let's take a peek at a couple now that we really haven't quite talked about yet. And that's going to be no solution and infinitely many solutions. So let's do a no solution with graphing first. Again, we're going to have to switch these to slope-intercept form in order to solve them. So we'll go ahead and get started with that right away. X minus y equals 4. Remember, I want to get it to slope-intercept form, which is y equals mx plus b. So x minus y equals 4, so we're going to subtract x first from both sides. Those will cancel. We'll have negative y equals negative x plus 4. Divide by negative 1. So that y ends up being positive 1y. Y equals negative divided by negative is a positive, so I just have x. 4 divided by a negative 1 would be a negative 4. So our first equation is y equals x minus 4. Let's look at our second one then here. Convert that. So remember, slope-intercept form is what we're looking for, so we're getting y by itself. So I'm going to move this x first. Add 3x. Those will cancel out on that left side. 3y equals 3x minus 6. Divide everything by a positive 3, and we would get y equals 3 divided by 3 is 1, so that's just x. Negative 6 divided by 3 is negative 2. So we would get y equals x minus 2. So let's go ahead and graph these and see what happens. So the first one, again, I'll do in red. Second one, I will graph in blue. So first line starts at negative 4. 1, 2, 3, 4. Remember, that's on the y-axis. That's what we call it, the y-intercept, where it crosses that axis. And then slope is just 1 over 1. Up 1, over 1, up 1 to the right 1. Go ahead and throw our line through there. And then our second line is at negative 2 is our y-intercept. And the slope is up 1, right 1, up 1, right 1. And we have something interesting that happens here. We have two lines, but they do not intersect. They're parallel to each other. So this means that they have no solution. Since they do not cross, and since they will never cross, they're never going to intersect at a point, so that means there's no solution to this one. And one way to absolutely know if this is the case is by looking at our slope and y-intercept. So if you're just given lines and you're not asked to graph it, sometimes you can just realize that it has no solution by looking at a couple of things. So in this case, the slopes are the same. They're both 1 over 1, and the y-intercepts are different. So if you ever have a case where the slopes are the same, y-intercepts are different, there's going to be no solution because they're going to intersect at different points, but their slopes or the rate of change that's happening is going to be the same. So that's why there's no solution. So let's look at one then using substitution or elimination. And in this case, I would definitely use elimination again because they're both in standard form. And I can already tell that this one's going to be easier to solve. So we have x minus 2y equals 7, and negative x plus 2y equals 7. So let's treat this as a addition problem. I already see that my x's are going to cancel if I add them together, and actually so will my y's, and we'll see what happens here. So this is why I'm just going to use addition to solve this. So I'm going to have 1x plus negative 1x, that's 0x, so that's just 0. So I'll just write it in this case. Then I have negative 2 plus 2, which is going to be 0, so plus 0, equals, and we have 7 plus 7, which is 14. If we add 0 and 0 together, we just get 0 equals 14. Now let me ask you this. Does 0 ever equal 14? Well, in this case, the answer is no. So if you're ever solving a systems of equations and you get one number equal to another number, such as 0 equals 14, then we know that there is no solution. This one cannot be solved. Or I shouldn't say it can't be solved. It can be solved. These lines just don't intersect because they're two different lines with different y-intercepts. I should say two lines, same slope, two different y-intercepts. So that one has no solution in this case. So those are a couple examples with no solution, both graphically and algebraically. So let's move on to our last type of problem then, which is infinitely many solutions. And let's use a graph to do this first. So again, we're going to convert these to slope-intercept form. X plus 3y equals 6. Going to subtract x, 3y equals negative x plus 6. Those cancel. To get y by itself, we must divide everything by 3. So y equals, this is negative 1 divided by 3, which is just negative 1/3. So 1 over 3, negative 1 over 3, times x. 6 divided by 3 is 2, so plus 2. And let's do that second one then. Negative 2x minus 6y equals negative 12. Add 2x to both sides. Those cancel, so you'll have negative 6y equals 2x minus 12. Let's divide by negative 6, divide by negative 6, divide by negative 6. Negative 6 divided by negative 6 is 1, so y equals 2 divided by negative 6 would be, well, if you divide both of those by 2, you would get negative 1 over 3. X, negative 12 divided by negative 6 is plus 2. So let's graph these and then let's see if we notice anything. So I'll do that one in red and this one in blue. First one is at a positive 2 for my y-intercept. Plot that. And it says go down 1, right 3, down 1, right 3. Slap a line through there. Arrows on the ends. Okay, so that was that line. Now something interesting is going to happen here. So my second line is at 2, and the slope is down 1, right 3, down 1, right 3. And draw your line through, and you should have noticed something happening. That these are the same exact lines. They have the same slope and same y-intercept. So that means that one line is right on top of the other. So this means that we have infinitely many solutions. And the reason for that is because those lines will go on forever, and since they're directly on top of each other, that means that they're going to have the same solutions all the way across them. So no matter what value we'd put in for x or y that falls on these lines, they're always going to be a solution to this. So that means there's infinitely many since the line goes on forever. So that's graphically what happens when there's infinitely many solutions. It means that the lines are exactly on top of each other. And just by looking at the equations, we can tell if one has an infinitely many solutions if your slopes are the same and your y-intercepts are the same. So sometimes if you're just looking at your equations, you can get a good idea as to how many solutions it will have. So let's take a look at our last one here then, which in this case we're going to use substitution because one of my problems is already solved for y here. Could be solved for x, but in this case it's solved for y. So I'm just going to go ahead and use that to my advantage. So what I see here is that y is the same as x minus 8. So I'm going to put this x minus 8 in for this y in my first equation in order to have an equation in one variable, which will be x, and then we'll go ahead and solve. So negative 16x plus 2 times, since it's 2 times y, it's going to be 2 times 8x minus 1. And that's going to be equal to negative 2. So we have a couple things that we need to do here. We need to use the distributive property, we need to combine like terms, do some subtraction or addition, and then some division, and we should get the value of x. So let's distribute first. So we're going to write down everything else I have. Negative 16x plus 16x minus 2 equals negative 2. Well, if we combine like terms on this side, negative 16x plus 16x is just going to give me 0x. So the only thing that I'm left with, since those cancel out, is negative 2 is equal to negative 2. Since we have one number equal to itself, we know that we have infinitely many solutions. Which means that both of these lines are the same exact thing. So if we were to change this top equation into slope-intercept form like this bottom one, we would see that we'd have a slope of 8x and a y-intercept of negative 1. So we had looked at this topic earlier in the year, but just with solving different types of equations. It does apply to graphing lines as well. We can have, like I said, one solution, no solution, so one solution, no solution, and infinitely many solutions. What that means is that if it has one solution, your system of linear equations, then it means that both lines intersect at one point. If it has no solution, it means that the lines are parallel and will never intersect. It also means that they have the same slopes, different y-intercepts, so something to look for even before solving a problem. And you also have infinitely many solutions, which means the lines are directly on top of each other, and they would have the same slope and same y-intercept, so something also to be looking for when working with that. So that was our lesson today on solutions to systems of linear equations. Remember, our goal or ICANN statement was I can identify the number of solutions a system of linear equations has by solving it using graphing, substitution, and elimination. So hopefully after watching this video, you're feeling more comfortable with using those three methods and understanding the different types of solutions that systems of equations can have. If you have any other questions, please feel free to watch the video or ask me for assistance.